Here we have another example which looks very similar to the previous one, but this time it's a two-tailed test because what we're looking to prove with the alternative hypothesis is that lambda is not equal to 10. We're not saying it's bigger, not saying it's smaller, we're just saying it's not 10. So we do what we did before. We say that x is belongs to the Poisson distribution, parameter lambda. The null hypothesis is that lambda equals 10, and the alternative hypothesis is that lambda is not 10. And the significance level, we can see, is 5%. So we don't know whether lambda is bigger than 10 or smaller than 10, we're just exploring the alternative hypothesis that it's not equal to 10. So it could be greater, it could be smaller, so because of that we've got a two-tailed test, and so the probabilities are going to be 2.5% at each end. So what we're looking for is the smallest number to start off with, where the probability of x being that number is smaller than 2.5%, and that's 3, because the probability that x is less than or equal to 3 is 0.0103. So if we look here, what we're looking for is the probability to be smaller than 2.5%. So obviously at 4 it's greater, it's 2.93%, but at 3 it's smaller, it's 1.03%. So the probability that x is smaller than or equal to 3 is so small, it's smaller than 2.5%, we would say that's not just luck, there's something would have changed. So if we found that x was smaller than or equal to 3, we would say that the parameter, it looks like the parameter has changed. So now we do a similar thing at the top end, but it's a little bit trickier at the top end because we've got to take away from 1. So these numbers down here, we've got to take away from 1, we've got to find the number to be smaller than 2.5%. So let's just do a little bit of guesswork. Supposing we said that maybe x is greater than or equal to 17. Well, 17, probably greater than or equal to 17, is 1 minus the probability that x is less than or equal to 16. And less than or equal to 16, we can see here is 0.9730. So it's 1 minus 0.9730, and that's 0.0270. So that's no good. We're looking for the number to be smaller than 2.5%. And remember that when we're looking for 17, we're looking at the number above the row above because of this business here. So anyway, 17 wasn't right, so let's try maybe x is 18. Maybe when x is greater than 18, it's less than 2.5%. That's 1 minus the probability that x is less than or equal to 17. Less than or equal to 17, again the row above, 0.9857, so it's 1 minus 0.9857, which is 0.0143. Yes, that's less than 2.5%. So the critical region, and remember with a two-tailed test there's two critical regions, the critical region is 0, 1, 2, 3 and 18, 19, etc, etc, etc. The critical values are 3 and 18. So these are the first numbers you come across when you enter the critical region, 3 and 18, so the critical values are 3 and 18. So here we've got the critical values being 3 and 18, and then we may be asked for the significance level. And if we're asked for the significance level of this, the significance level is these two probabilities, 0.0103 and 0.0143 added together, and that works out to be 0.0246. So this is the significance level of these critical values. Here's a similar example, but this time we've got a binomial distribution. So we're testing to see if the null hypothesis is true. Null hypothesis is that p is 0.3. Alternative hypothesis is p is not 0.3. So let's do what we normally do. What distribution have we got? We've got a binomial distribution. So that's 40p. The null hypothesis is that p is 0.3. That's a 0 there. The alternative hypothesis is that p is not 0.3. And the significance level this time is 1%. So because what we're testing is p is not 0.3, it's a two-tailed test. So we're looking at halving that 1%, so that's 0.005. So we're looking in the p being 0.3, that's here. We've got 40, we've got 0.3. We're looking for 0.005. So we go down there, we can see that at 4 we've got 0.0026, and at 5 we've got 0.0086. So we're looking for the probability to be less than 0.005. So 5 is too big, so 4 is going to be the critical value. So the probability that x is less than or equal to 4 is 0.0026. Remember, it's a two-tailed test, so we're halving 1%. Half of 1% is 0.005. 0.0026, that's less than 0.005. 0.0086 is bigger. So our critical region is going to be 0, 1, 2, 3, 4, and the critical value is going to be 4. Now we need to look at the top end. So at the top end, remember that 1 minus 0.005 is 0.995. So we're looking down the 0.3 column for 0.995. Here we've got 0.997. Here we've got 0.993. So at this point we've got probability that x is less than or equal to 20 is 0.9976. And so that is the first time, 0.9976 is the first time that the probability goes above 0.995. But remember, we are looking at the row above, so it's actually the probability that x is greater than or equal to 21 is 1 minus the probability that x is less than or equal to 20. Less than or equal to 20. So because of that, the critical region is 21, 22, and so on up to 40. So the whole critical region is 0, 1, 2, 3, 4, and 21, 22, and so on up to 40. So the critical values are 4 and 21. So if we're asked for the significance level, then we need to add those two numbers together, which works out to be exactly 0.005. So we had a 1% significance level on this question, and we've ended up finding probabilities which are actually half of that, 0.005. Sometimes they ask questions which don't say they want it to be less than 1% significance level, but to be about 1%, the significance level to be about 1% or 5% or whatever. But in this case, supposing the question said test the null hypothesis at approximately a 1% significance level, and then we'd need to find the best critical region. So if this were the case in this question, we could get nearer to 1% by taking one closer value in the critical region. So we're looking down the 0.3 row here. What we had before was 0.9976, but here look, there's a 0.9937. So the probability that x is less than 19, less than or equal to 19, is 0.9937, so the probability that x is greater than 20 is 1 minus that, which is 0.0063. So if we were looking simply to make it as close to 1% as we could, our critical region would be, let's just write this out, the critical region would be as it was before, which was 0, 1, 2, 3, 4, and the numbers from 20 up to 40. And our significance level would be the 0.0026 we had before, this one here, but this time plus 0.0063. So we'd get 0.0063 plus 0.0026, that will give us 0.0089, which is closer to 1% than the half a percent we got here. That's just a twist they may put on the question. That's something that you need to be aware of.